Start the new section today, which is on queuing theory, and it sort of gets a bit more mathematical at this stage, and so it'll start a little bit simpler today, and then progressively it gets a bit harder. Okay, so I'm just going to start very simply with queuing theory. What is it? And then we'll go over a very simple, intuitive but powerful result called Little's law. And then we'll talk about the basis of queuing theory, which is stochastic processes, explain what it is, some types of stochastic processes, and we'll focus on a specific type of stochastic process called a Markov process, try to explain why it's important, and hopefully you'll understand Markov processes pretty well by the end of this. And then if I have time, I should be able to do homogeneous Markov processes, and most likely I won't be able to get to the Chapman-Kolmogorov equations. If I can, I will, otherwise we'll continue with that on Thursday. All right, so what is a queue? What is queuing theory, generally speaking? So queue is, it presupposes two entities, a server and a client or a customer, and we represent servers like this, and we actually don't represent clients. What we do represent is a queue, which is drawn like this, with essentially a place where customers can wait. And in the simplest case, you can think about it, is, for example, you go to the Tim Hortons, and that's the longest queue you see around here. And there's a service person who is servicing a request. That's the Tim Hortons service person. And this is the corridor where everybody's sitting, and of course you're the customers. Now, what happens, right? Let's imagine the following situation. Let's say there was no queue, all right? So you go to Tim Hortons, and either there's, you can get service right away, or they say, well, go away. Essentially, there's no space. So there's one person who's being served. Perhaps you can represent it like that. Not in the queue, being served at this point. And then if that person is busy and they go to the queue, you're just thrown out. You can't go in. And this is not as silly as it sounds. Imagine a plane now, right? You don't have a queue of people waiting to get onto an available plane. You have a reservation. You get in the plane. If you're in the plane, you're being served. And if you go to the plane and there's no space, well, you're not being served. There's no queue per se. It just is or is not. We are not interested in plane-like situations. We're interested in queue-like situations where there is a server and there's a customer. Now, one of the things you need to understand about queues is that queues go with buffers. There is a storage space. This is called the queue or the buffer. And what's being stored in here are service requests. Or in some cases it's customers, but more generally when we talk about computer systems, we're talking about service requests that are being stored over here. Now what you have to realize, and this is just common sense, you don't need queuing theory for this, is that let us say that the service rate over here is intrinsically some rate of service. We'll draw that represented always as mu. That's called the service rate. And correspondingly, we have a rate at which customers enter the system called the arrival rate. And we represent this as lambda. The intuitive and obvious observation is that mu has to be greater than lambda, or at least greater than equal to lambda. And this is, as I said, you don't even need queuing theory for this. This is just obvious common sense. Why? Because if mu is smaller than lambda, then there's always going to be more people arriving than can get served. So this queue is going to become infinitely long over time, and so we call that system unstable. Okay, it's an unstable system when the service rate exceeds the arrival rate exceeds the service rate. Okay, so we don't want to discuss unstable systems. We're really talking about stable systems where lambda is less than mu, and later on we'll see actually a proof of stability, etc., where lambda is less than mu. But this is just common sense. You don't really need you don't need to be very smart to see that happening at all. So that's the first observation I want to make over here. The second observation I want to make over here is, again, this is something that's not in the lecture notes. Probably I should put it in. But in computer networks, what is the role of buffers, right? So we automatically assume, at least we meaning the networking type people, assume that all routers and switches and service elements such as those have a buffer with them. What is the buffer for? The buffer is basically only to deal with transient overload. Okay. In other words, what a buffer does is that there is a mismatch between the arrival and the service rate. The arrival rate is less than the service rate. You have to remember that it's not the case that the buffer is there because the arrival rate is greater than the service rate. No, the arrival rate on average is guaranteed to be lower than the service rate. Okay. However, there are some periods of time where the arrival rate and the service rate are out of whack. Okay. For example, just take a practical example over here. You go to Tim Hortons. In general, the arrival rate is less than service rate, right? It's obviously the case that the queues are not going on to infinity, right? What's going on is that there are bursts of arrivals. There are periods of time when a bunch of people come. So class ends, everybody wants to go get a cup of coffee. They all arrive to the queue, to the server, essentially at the same time, and then they all get stuck in the buffer, and then they get served, and then the queue disappears. Okay, so we have this, situation where the arrival rate and service rate are temporarily out of whack. If we were to draw a figure like this, time on this axis, we can think of the service rate as being something like this. I'm just ignore the y-axis for now, and what we're seeing here is that, or maybe I should draw it the other way. So this is the service rate. In some sense, the service rate has some mean like this, and the arrival rate has got some mean like that. And for some period of time, service rate is below the arrival rate. Okay, so or potentially the arrival rate is much higher. I guess what am I doing over here? This is the other way around. The arrival rate over here is higher than the service rate. It's higher over here. I need different colors to do this properly, and out of colors. Let me draw this once more. And let's see. So that's the mean. I want to make this a mean arrival rate, and I want to make this the mean service rate. So that's above. And let's say this has some variation over this. And what I'm basically saying there are periods of time like this section over here where the arrival rate exceeds the service rate. Okay. Similarly, this section over here. Notice it goes below the mean as well. It's just that, you had these temporary glitches over here. Same thing over here. So these three periods are periods where the arrival rate temporarily exceeds the service rate. I want to focus on the fact that it's a transient overload. It is not persistent overload, because persistent overload is not stable. Okay? So queuing theory focuses on this specific phenomenon, the transient overload phenomenon, that allows us to compute certain metrics of interest about this transient phenomenon. Again, some of you came in late, so I just want to emphasize this, because this is where you can go wrong. If you don't have the right foundation, you can just go wrong. The purpose of buffers is not to deal with persistent overload. You will never, ever solve persistent overloads. Okay? First point. Second point, transient overloads happen because the arrival rate, which is this instantaneous arrival rate, exceeds instantaneous service rate. So queuing is by definition a transient phenomenon. Okay? And third, queuing theory is looking at the behavior of this transient phenomenon. Right? And so if you have a persistent overload, the only way out of that is to increase capacity or decrease demand. So how do you increase capacity? You bring on more servers into Tim Hortons. If you decrease demand, how you do that? You basically throw people out, or you raise the price of coffee, and then people won't drink as much coffee, and then the demand goes down. Or we have what are called discouraged customers. They see the queues long and say, I don't think I want coffee anymore. I'd rather just go, I'd rather not do this, right? So we have discouraged arrivals, and then what happens? Arrival rate kind of goes down because we have discouraged arrivals. We will study some of these phenomena, not all of them further on, but I just want to get this point across, very, very strong, that we're studying transient overload. Okay? Any questions about this so far? Okay. Alright, so because most queuing theory textbooks and most queuing theory analysis and everything acts as if queuing is always going to be there. No, it's just a temporary thing. It may dissipate in milliseconds or microseconds or seconds. It's not going to last very long. We don't want it to last very long. In some sense, queuing already is a bad thing. Okay, you don't want to have queues. Okay, so if some router vendor comes to you and says, I have a gigabyte of buffering in my switch, I'm a great switch. You're saying, why? You're catering to a phenomenon that should not exist. That means the service rate is so bad that you need to put lots of buffers to accommodate the variations and arrivals. Okay, I'm being a bit facetious here. There's a very, very interesting ongoing debate on what is the right amount of buffers for switches, and I'm selling it way short with this remarks here. But the point I want to get across is just that it's transient. Okay, let me give you some examples of queuing in the networking world. So, as I said, switches have buffers. The normal way to represent a switch, this is if you have, let's say, let's do a simple 2-port switch, because I don't want to draw too much. So how do you draw a 2-port switch? You have 2 input ports, you have 2 output ports. Now, of course, the input and the output ports are the same thing, right? We just kind of open the tap to make it easier to draw. And typically what we have is that, so we have 2 network interface cards. We have an input queue over here and a little server, and we have an output queue over here with its servers. And then we have some cross connect, which is drawn typically like this, like a X, and we draw this cross connect over here. And well, here we have 4 queues. We have 4 queues because stuff comes in the link, it gets stored in this buffer awaiting service, and then at some point the cross connect fabric says, okay, I have space, I can transfer something to the input. It goes to the input to the output, it goes and sticks in another queue over here, and it waits for the link to be free, and then off it goes. So we have in fact 4 queues in a typical 2x2 switch. Of course, if you have an 8x8 switch, you have 16 queues. So if you have you have n inputs and m inputs and m outputs, you have 2 m queues, and you have fabric. If the fabric is buffered, then you have more queues inside the fabric. So switches and routers tend to be real fertile grounds for queuing theory, because obviously there's a lot of queuing going on. So that's one practical example. In fact, this is an example that motivated quite a bit of research in queuing theory. So the queuing theory started out as being part of logistics and operations research in the 40s and 50s, I guess, when people were trying to look at transshipment of goods and and logistics operations in wars. But with the development of network processors and routers, queuing theory now is essentially dominated by computer type people and networking type people. Okay, the second kind of system where you can have a setup like this is a typical web server. So we have a web server, and when we have how does it look like? We have some kind of storage which has some content in it, and we're trying to load and store content, and then we have a set of machines, and we have a large set of machines. We have the internet, and then all of these guys are making requests to the web server. Typically the web server will have a buffer where it's waiting for incoming requests, and it fetches a request and off it goes. That's another queue. Again, the analysis of this system is quite interesting, and in just about 15-20 minutes from now we'll look at some numerical example for precisely this kind of web server. Okay. Finally, a system that has been studied a lot is the phone system, and here we don't have requests that are computers, but they're coming from phones. Now, forever and ever, phones are represented in this fashion, right? And actually, I don't even know if people of your age have even seen phones that look like this, right? A traditional, like a base with this big plastic thing that you hold in your hand. My kids have never seen a phone like this in their whole life, actually. For them, they're just used to cordless phones, and no doubt 10 years from now, kids will say, you mean you have a phone wire? What is that phone jack for? I don't know what it's for, because they'll all have cell phones probably implanted in their brain or something like that. Nevertheless, all of us older people who remember this stuff draw phones like this. It's this traditional black base. You can only get one color, it's black, and handset on top. So I'll draw that. So essentially these guys are connected to what's called a switch, and what you do is Oh, I forgot the little dials. Dialing a number, whoever thought of that? I mean, you can't just speak into your phone and have it call? It's like, wow. Anyway, so you pick up the thing and you dial this number, and what happens is it goes into what's called the call processor at your local central office. And what's going on is it's a request to make a connection to some destination. Of course, multiple people may be making calls at the same time, and we want to look at the queue of requests. In the modern age, the corresponding phenomenon is this. You leave the class, all of you want to call your friends, you all flip open your cell phone, and you say, you speak, or you dial the number, or whatever it is, or FEEP, the correct term is FEEPing the number in. I bet you didn't know that. Because when you press this keypad, what you send out is a frequency pulse. So the accurate technical term for pressing a number on your keypad is FEEPing. And, so you do this and you get a busy signal. You say, oh, the cell is overloaded. Same thing, call processor tries to make multiple calls, and so we have an overload of arrivals. And when the arrivals overloads the service rate, the number of calls that can be carried in that particular cell, you get a denial of service, or in this case a denial of service, or you have to wait for a while for your call to go through. You have a fairly long time, it can be several tens of seconds, and that is nothing more than a transient overload under queue. So I'm just giving you some examples of queuing system just to kind of get your head around this over here. Okay? Any questions about this? Beg your pardon?
This is not a queuing.
Why is it not a queuing system?
Isn't it like kind of the airplane example? If you can't get in, you have to get out and wait?
No, there is a sort of a set of, you can hold calls for a certain duration of time before you say, okay, it's busy. Yes, you're right. I mean, you can build it which has no queues. If you're incoming service request, you just say deny service if there's no available request. But you can hold it for a few seconds. Hopefully somebody's finished the call. It's a better thing to hold it for a few seconds than to immediately say no. So, yeah. So yes, so you can build it that way. Any queuing system can be built with zero buffers, right? And then you can say, okay, this is a reservation-only system. But you do actually have a little bit of capacity in there. It's good customer services to have the call go through, even if you have to wait 10 seconds then to send them a busy signal right away. I beg your pardon? You can get a call back, yeah. Yeah, you can get a send request and that will go to some other process and then it will call you back or whatever. There are many things you can do, but okay, we don't want to go on that path. There's extra cost for everything. That's where the phone network works. Okay, so while we have this here, now we want to start looking at some metrics of interest. So let me just write down some metrics. So first metric could be, for example, the queuing delay. This is so what we do is we take this queue, we'll take this queue over here, and let's say the customer enters at some point, we mark it, we'll paint it red, and then we just wait how long before the customer exits the system, that same mark tag exits the system. That is called the queuing delay. Okay, so it's obvious. The second thing is the backlog. It's the mean number of, basically there's a mean queue length. Okay. So what is the mean queue length, right? And of course, what I was saying earlier was that when you have the lambda greater than mu, then you have an infinite backlog. Okay, it's an unstable system. Third thing is the fraction of time the server is busy. And this is also called the utilization. And again, for obvious reasons, you want the utilization to be less than 1. And we have the drop rate. In other words, how often does a customer or a service request arrive when the queue is full? Okay, if the queue has finite capacity. Now, we also study infinite capacity queues, but for finite capacity, we can look at the drop rate. And finally, we can look at the mean busy period. In other words, given that the queue is busy, how long did the busy period last? Okay, and one sign that things are going bad is that the mean busy period is growing over time. If I'm measuring the busy period of a switch or some server, and if the busy period is keep on going up, then I have pretty good sense that my queues need to be, managed better. Okay, so that's one good indicator. All right. So it turns out that we can compute these metrics. So it's a good news. We can compute these metrics even though it's a transient phenomenon and it can be fairly tricky to analyze. The good news is we can analyze them. But there's a big bad news. The big bad news is we can only analyze them when the arrival patterns are mathematically nice, or more precisely when they're Poisson. Okay, so what does the Poisson mean? The Poisson means that the number of arrivals in a certain time period follows the distribution e to the minus lambda, lambda to the n by n factorial, so standard Poisson distribution. So we want the inputs to be Poisson, and if the inputs are Poisson, then we will give you all the metrics. All right, but the inputs are not Poisson, then we know less. And if the service rate is not what's called exponential, I'll come to that later, we know even less. So the general queuing system, which is essentially not characterizable. Okay, we can give very, very weak characterizations of the general queuing system. Okay, in fact, almost the only thing we know is Little's law, which we'll come to in just about a few minutes from now. But other than Little's law, there's very, very little we know about general queuing systems. So good news is we can give you metrics, we can compute these things. Bad news is input has to be Poisson. And it has been shown, as I mentioned earlier, that in fact traffic is not Poisson. So why are we studying queuing theory? What's the whole point? Okay, so the two good reasons for doing this. The first thing is that understanding queuing theory from a mathematical perspective, even assuming Poisson inputs, gives you intuition, gives you insights. Okay, you kind of get a feel for how these queues are going to behave, how these things are going to be put together. Okay, and as people working in the area of networking, as people who are working in the area of not even if you're networking, but anything that uses stochastic processes, it's good to have this intuition. Intuition is worth a lot. The second reason why it's good is that you can get numbers out of it. The numbers may not be completely correct, but they're sort of within an order of magnitude correct. Okay, so you cannot use queuing theory or queuing theory as we know it today to say, well, the airport lounge should have exactly 50 seats or whatever it is, right? Or the buffer size should be exactly this. No, it will say, according to Poisson arrivals and so on, the buffer size should be, let's say, 50 seats. It means that if you put in like 75, it's okay. You don't need 500, you don't need 5,000. So it's sort of ballpark, order of magnitude kind of stuff. And it's very good for that. So for these two good reasons, it's worth studying. Now, I should also mention that when I was going to grad school, I did my PhD at Berkeley, there was sort of this sentiment that you don't need to study queuing theory because who cares? At least in the computer science department, we were not encouraged to study queuing theory, and there was not even a course offered in queuing theory. And I had this attitude for many years afterwards that who needs queuing theory? And when I wrote a textbook 12 years ago, I basically stated in the book, who cares? We don't need queuing theory because all the assumptions are wrong. And I've had to change my perspective 180 degrees because I now have come to realize that even though everything I said there was true, yes, all the models are wrong and we know it, yet the amount of intuition you gain is well worth the effort, and it is quite a bit of effort. It's not easy, it's not straightforward. We're going to make it as easy as possible, but queuing theory is hard work, but I think it's worth it because of these two reasons. Okay? Any questions at all about this? Yeah. Okay, so let's start. So that's queues and kind of a high-level view of queuing. Let's start with Little's law. All right, and I'm going to leave this up because I'll need that. So Little's law was this law stated back in 1951 by J.D.C. Little, and it's a law that's so simple you don't need any maths to write it. You can just write it like this. You can say, and let me make sure I'm using the right terminology, mean number of customers in any queuing system, okay, is equal to the product of the mean waiting time times the mean arrival rate. And that's it. So I can tell you that the mean number of customers is a product of these two quantities. So let's see what it means intuitively. So mean waiting time is the amount of time you're spending waiting in a queue. So you go to Tim Hortons, you sit there, you wait in line for 20 minutes or whatever it is, so 5 minutes. That's a mean waiting time. That's your waiting time. And the mean waiting time is this waiting time across all customers. And then here the mean arrival rate, the rate at which people join the system. And if you multiply these two, you'll actually find out how long the queue is on average. So some people find it very intuitive. It's obvious. Why is it obvious? Well, you pick any particular guy coming in and you paint that person red and they join the queue. Okay, this is some person chosen at random. That person is going to wait so much time to get to the end of the queue, right? And in that time, how many people came? These many people came, right? Multiplied with this time is the number. And so that's how the queue is going to be, right? So that's pretty intuitive. And so some people find it intuitive. At the same time, it's also considered fairly deep result because it holds true no matter what the arrival pattern is. Okay, I don't care what the actual pattern of arrivals is. In fact, I don't even care what the actual service rate is. Okay, the services can be, you might not say that the people are served first come, first served. You can say, okay, we're going to skip the first guy, pick the second guy, then the fifth guy, we're going to serve all the alternate people, first all the odd people and the even people, whatever. You can say, serve all the tall people first, and then the medium height, and then the short people. And serve in order of height, it doesn't matter, okay? It doesn't matter. You can serve it any order you want. People arrive in any order they want. Yet, this relation holds true because, we've got this waiting time sort of encapsulates all of the variations in service. Okay, the mean waiting time averages across all possible variations in service, and the mean arrival rate averages across all possible variations in arrivals. So the system, this equation is essentially insensitive to these two things, which is wonderful. And so this is pretty much all we know about general queues. Okay, this is a sum total of knowledge after 60 years of work about general queues, without knowing much more about arrival rates and the, first and second and third moments of their distributions and so on and so forth. Is pretty much all you can say over here. And it actually is useful. So let me first put a little bit of notation just so that it makes it easier for me to write. So I'm going to denote the mean waiting time as T, and I already said the mean arrival rate is lambda, and we'll call this as N, the mean number of customers, and we can just write that N equals T lambda. Okay? So let me do one example, and then we'll take a break, and then we'll do another example, so that we're not going to be too far off in the example. So the example I have is something that you probably are used to, which is you get email all the time. You're sitting there, and email keeps pouring in. I get roughly about between 60 and 100 messages a day, every day. Okay, and these are non-spam messages. Okay, the amount of spam messages I get, I don't even know because they get filtered out. So they're lost. I'm getting 60 to 100. So I guess, or let's say you get 12 messages an hour, which is not too bad. Okay, well, it's about 100 messages a day, assuming that you have an 8-hour working day. 12 messages an hour is about right. And I'm saying that you read your mail once an hour. There's actually a little bit of time management advice hidden in this example, which is that people have found that if you are in the habit of checking your email as soon as it arrives, or worse, kind of hitting, get send and receive, or whatever the equivalent is in your reader, and you read mail all the time, it's equivalent to somebody knocking on your door, okay, 12 times an hour, saying, here I am, help me. Here I am, help me. Every 5 minutes, somebody's going to come and knock on your door. The time it takes for you to context switch your short-term memory out and swap in the corresponding whatever information you need to handle messages can take you up to 5 to 10 minutes, depending on how fast your context switch time is. Okay, so let's say it takes you 5 minutes of time to change context, answer the email, and change back. You are essentially doing no work. Okay, you're just doing context switching back and forth, back and forth. At the end of the day, you say, great, I was very productive at work. I answered 60, whatever it is, 100 email messages. But you know what? You got no work done. In particular, you did not do the homework for this course. Okay, So the answer, what you really should be doing is read mail once an hour, because you context switch once and then you handle all your email and then you shut it down. And ever since I did this, I refuse to read email faster than once an hour. My productivity has gone up. That is why I can write this book. Okay, so anyway, let's go back to Little's law. And what you're saying is that what is the average time a message is unread? Okay, now it turns out that this one you can solve quite intuitively, but let's just use Little law anyway. All right, so we have 12 messages an hour, so our mean message arrival rate is 12. In fact, it is deterministic because it's so 12 an hour is my arrival rate, and I read mail once an hour. If I read mail once an hour, then I know that the actually the question should be yeah, okay. So the mean number of unread messages, okay, is what? Okay, so I'm going to be getting 12 an hour, and then I have to sit and wait roughly half an hour. So the mean number of customers, which is the mean queue length, okay, is going to be 6. Okay, why is that? Because you can imagine that this is 1 hour and I have these 12 things coming in. Okay, so the average, okay, is essentially what happens in this time over here. Okay, so I'm going to have 6 waiting in the queue on average, the mean length of the queue. I'm going to have 12 waiting for me, but the mean length of the queue is basically 6. Why? Is because if you want to draw it this way, this is time, this is number of messages, and it goes up linearly from whatever 0 to 12. So the mean obviously is going to be 6. So mean number of customers is 6, right? And so I'm going to ask, what is the mean waiting time? What is the average time a message is unread? Okay, and well, you can do the math and you'll get that this equals 30 minutes. Okay, so it's a pretty straightforward thing. Okay, or you can say, if you don't understand this, but you can say I have mean arrival to 12 an hour, and I can tell you the mean waiting time for a message is 30 minutes because the total time is 1 hour. So on average, you're going to wait 30 minutes. Then I can plug these two in. I can tell you that on average, I have 6 messages in the queue. Okay, in fact, every time I observe it, it will have 12. Okay, but on average there were 6 in the queue. So if I take any random point in this interval and I sample the number of messages in the queue, the number I'm going to get is 6. Okay, so you can kind of use it either way. All right. Any questions about this over here? So this is again, this is just giving you a simple explanation of why we have this kind of situation here. All right, let me pause here, and we'll take another application of Little's law and then derive it before we go on to stochastic processes. Okay, any questions about this over here? Relates these two quantities, the mean number of customers, mean waiting time. Let me try and use it for a practical example, and again here I'll show you how we can use queuing theory, or in this case Little's law, for kind of approximate seat of the pants kind of analysis. So let's say that we have a web server, so I'll put the parameters here as before, and I'm going to just go with the numbers here. Okay, so I have lambda equals, let's say it gets 10,800 requests an hour. Okay, now you'll say, well, which hour, right? Obviously web servers are going to be busy sometime and idle sometimes. All of the analysis for what's called teletraffic systems, by the way, if you want, you can sit here, because there's a seat over here, on any of you guys in the corner, because you can't see this presumably. Okay, you can come there if you want. Anyway, so we take what's called the busy hour average. So what you do is you measure the system and you find the hour of time that is the most heavily used, and you look at the busy hour. And so this you can do it for the busy hour. So whatever time, it could be 9 a.m. or 5 p.m. whatever. So we want this 10,000 requests an hour, and this corresponds to, of course, to 3 requests per second, which is why I chose that number. And the second thing we want to know is that we want the mean waiting time less than equal to 6 seconds. Okay. So, all right.